Before we can apply the stiffness method to analyze a frame, we have to compile the structure stiffness matrix. And so we will do that for a coplanar or 2D frame in this problem. The key concepts we'll use are calculating the member global stiffness matrix for a frame member and combining member stiffnesses to obtain the structure stiffness. And here's our frame. It has a pin support at node 1, a roller support at node 3, and node 2 is a fixed connection. That is a rigid connection that will hold its angle as the structure deforms. We are given the cross-sectional area, moment of inertia, and modulus of elasticity for the frame members, and it's identical for each member. And our goal is to determine the structural stiffness matrix. And here's our approach. We begin by calculating member stiffnesses. Then we assemble those stiffnesses to construct the structure stiffness. Now, the structure stiffness matrix is usually an intermediate step to applying the stiffness method. So there's no good approximate analysis tool we can use to determine whether we have reasonably created our stiffness matrix, but what we can do in step 3 is check symmetry of the matrix. The structure stiffness matrix should be symmetric about the diagonal. If it's not, that's a sign that we've made a math error somewhere. So let's begin. We'll start with member stiffnesses. And let's start with member 1. Member 1 has the near node as node 1, and far node is node 2. Its length is 12 feet, which is 144 inches. Directional cosines, lambda x is the change in x coordinate divided by the length, and the x coordinate does not change, so lambda x is 0. Lambda y is the change in y coordinate from near node to far node, and that's a positive 12 feet, divided by the length, and so lambda y is plus 1. For a coplanar frame element, the member stiffness matrix will have 3 plus 3, that is 6 degrees of freedom. So the matrix is 6 by 6, and we can find it written as a formula, equation 16-10, from our text. Within this matrix, we see the directional cosines showing up sometimes by themselves, sometimes multiplied by each other, sometimes squared. And we see repetition of other terms, AE over L, 12EI over L cubed, 6EI over L squared, 4EI over L, and 2EI over L. So let's calculate those terms for member 1. AE over L. Well, A for our frame, each of our frame members, is 30 square inches. E is the modulus of elasticity for steel, in this case, 29,000 ksi. And the length, we said, is 144 inches. So together, that gives 6042 kips per inch. 12 EI over L cubed is 29,000 ksi. The moment of inertia for the members of this frame are both 700 inches to the fourth, all divided by the length, 144 inches cubed. When we evaluate this expression, we get 81.6 kips per inch. Now 6 EI over L squared. We have the modulus elasticity of steel, moment of inertia for the members, and our length, 144 inches squared. This evaluates out to be 5874 kips. 4 EI over L (700 inches to the fourth) over the length, 144 inches, equals 56,3,900 kip inches. And 2 EI over L will be half of that quantity, but I will write this out longhand. And that gives us 281900 kip inches. Let's use these values along with the fact that lambda x equals 0 and lambda y equals 1 in our expression for little k, the frame element stiffness matrix, and construct little k 1. Which will have 6 rows and 6 columns. Now for element 1, the near node degrees of freedom are in the sequence 8, 9, 5, and then the far node degrees of freedom are in sequence 1, 2, 3. And our rows will also be in degree of freedom sequence 8, 9, 5, 1, 2, 3. Now for our first term. As we look at this equation for the element stiffness matrix, remember all the lambda x's will be 0. So this term will be 0. But we'll need this, and lambda y squared is still 1. Lambda x is 0, so this term is 0. This component is 0. This whole term is 0, as is this one. This component is 0. This whole term will be 0. as will this one. This component will be 0, and this whole term will be 0. We have this one. This term will be 0. We'll have this one, and remember lambda y is 1, so we can ignore the lambda y's. This one will be 0. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, and 0. So that saves us a lot of work. So in the top left corner, the coefficient will be 12ei over L cubed, as will the first row, fourth column, only it will have a minus sign. And we saw that 12ei over L cubed is 81.6 kips per inch. So we have 81.6 kips per inch in the first column. In the fourth column we have minus 81.6 kips per inch. The second and fifth columns, first row, will be 0, and then the third and sixth columns will be a minus 6ei over L squared, where 6ei over L squared is this quantity. So we have 0 minus 58.74 kips, 0 and minus 58.74 kips. Now the second row. The first, third, fourth, and sixth columns are all 0. The second and fifth columns are AE over L, this one positive, this one negative. And AE over L was this quantity. So we have 0, 6042 kips per inch, 0, 0, negative 6042 kips per inch, and 0. Our third row. First column is minus 6ei over L squared. Fourth column is 6ei over L squared. And 6ei over L squared is 58.74 kips. Fourth column is a positive 58.74 kips. The second and fifth columns are both 0. Third column is 4ei over L, and the last column is 2ei over L. 4ei over L we found to be this quantity, and 2ei over L we found to be this quantity. So we have a 0, 5,63900 kip inches, a 0, and a 2,81900 kip inches. Now our fourth row. Our fourth row is identical to the first row, but all signs reversed. Likewise, the fifth row is exactly the same as the second row, but with all signs reversed. So we have minus 81.6 kips per inch, 0, a positive 58.74 kips, a positive 81.6 kips per inch, 0, and a positive 58.74 kips. And then for the fifth row, we'll have 0, minus 6042 kips per inch, 0, 0, a positive 6042 kips per inch, and 0. First column of the last row is a minus 6EI over L squared, and the fourth column is a positive 6EI over L squared. So we have a minus 5874 kips and a positive 5874 kips. The second and fifth column entries are both 0. The third is 2EI over L, and the last is 4EI over L. So we have 0, 281900 kip inches, 0, and 563900 kip inches. Now let's check symmetry for this element stiffness matrix, and let's check that the diagonal is non-negative. All the diagonal terms are positive. That's a good sign. As we check mirror across that diagonal, all of the terms are coming out to be same magnitude and same sign. So it is symmetric. That's an important intermediate check. Now member 2. The near node for member 2 is node 2. The far node is node 3. The length of the member is 12 feet, and so that is also equal to 144 inches. Lambda x, directional cosine, is the change in x coordinate, that's 12 feet, divided by the length, and so lambda x for this member is +1. Lambda y is the change in y coordinate, which is 0, divided by the length, and in this case lambda y is 0. Now we'll use the same formula to create the element stiffness matrix, and so we know that we'll need certain quantities. One of them is AE over L for this member, and it has the same A, the same E, and the same L as member 1, so this quantity did not change. We need 12 EI over L cubed. E, I, and L are all the same for member 2 as they were for member 1, so we've pre-calculated this one as well. And I'll go ahead and complete our list using the values we calculated for member 1. Since that saves us some time. 5, 6, 3, 9, 0, 0 kip inches, 2 EI over L, 281900 kip inches. Now let's use these along with our new lambdas. Lambda x is 1 and lambda y is 0, along with equation 16-10, so that we can construct the element stiffness matrix. Element stiffness matrix for element 2 will have 6 rows and 6 columns. That's consistent for all coplanar frame elements. And our degrees of freedom for the near node are in the sequence 1, 2, 3, and then the far node 6, 7, 4. And the sequence I counted them out at are set by the headings on our formula. I chose to number my original degrees of freedom that way because it will make application of the stiffness method a little bit easier for me, but we'll see that in the next example problem. The rows will be associated with the same degrees of freedom in the same sequence. Now for our first row entries. For this element, lambda y is 0. So if we eliminate all of the terms with lambda y, we can save ourselves a little bit of calculation work. And notice that lambda x is 1, so whether it is by itself or squared, it still has the impact of being 1 times the quantity, and so we can ignore its presence in this equation for this element. So for the first row, we're left with AE over L and minus AE over L. The rest of the entries are 0. And here we had minus AE over L, and the rest of the entries for this row are 0. Next row. The first and fourth columns are 0. The second and fifth columns are 12 EI over L cubed, only this one is negative. And the third and sixth columns are 6 EI over L squared, both positive. So we have 0, 81.6 kips per inch, 58.74 kips, 0, minus 81.6 kips per inch, and a positive 58.74 kips. Now our third row. The first and fourth terms are 0. The second and fifth terms are 6 EI over L squared, only the fifth column has a negative sign. And then we have 4 EI over L and 2 EI over L. So we have 0, a positive 58.74 kips, 56.3900 kip inches, 0, a minus 58.74 kips, and 2 EI over L, 2.81900 kip inch. Now row 4. Again, row 4 is identical to row 1, but all signs reversed. And row 5 is identical to row 2, but all signs reversed. So we have a negative 6042 kips per inch, 0, 0, a positive 6042 kips per inch, 0, and 0, and then negative sign of row 2, 0, minus 81.6 kips per inch minus 58.74 kips, 0, a positive 81.6 kips per inch, and a negative 58.74 kips. And then our final row. Our first and fourth terms are 0. Our second and fifth terms are 6EI over L squared, but this one has a negative sign. And then we have 2EI over L and 4EI over L. So we have 0, 58.74 kips, 2EI over L, 28.1900 kip inches, 0, a minus 58.74 kips, and 4EI over L, 563900 kip inches. We check the diagonal. All the terms are positive. Good. And we check symmetry about that diagonal. And sure enough, it is symmetric. So that's a good intermediate sign. Now we're ready for step 2, where we assemble the structure stiffness matrix. And that'll be denoted by capital K. And so we'll sum the two little k's based on degrees of freedom. And what I mean by that, for example, the top left corner of the structure stiffness matrix, K11, where it refers to force generated at degree of freedom 1 due to deformation at degree of freedom 1. And we obtain that by summing the 1, coefficients from the two elements. And so if we look back for member 1, K11 is not this quantity, it's this row, the row associated with degree of freedom 1, and column associated with degree of freedom 1, it's this coefficient. And for member 2, degree of freedom 1 is this quantity. Put those two together, and we get 61.24 kips per inch. Now as we look at this frame, note that we'll get contribution from multiple members only if multiple members share those degrees of freedom. So in the case of 1, it's 1 degree of freedom. Both members meet at degree of freedom 1, and so both contribute. K16 will get contribution only from member 2, because only member 2 connects both of those degrees of freedom. K86 will be 0, because no single member connects those degrees of freedom. So as we look at our structure, the only degrees of freedom where the structure stiffness coefficients will be a combination from both elements are the degrees of freedom 1, 2, and 3. So let's calculate those out here. We'll go to 1, 2 next. We know that we'll get it from each of these two elements. From element or member 1, row 1, column 2 is 0. And from member 2, row 1, column 2 is 0. So this coefficient, 0 plus 0, is 0 in the structure stiffness. Now coefficient 1, 3. Again, that means force at degree of freedom 1 due to deformation at degree of freedom 3. From member 1, row 1, column 3 gives us this coefficient. And from member 2, row 1, column 3 adds in 0. So we have 5874 kips plus 0. So our stiffness coefficient is 5874 kips. Now, our second row, K21, from member 1, 2, 1 is 0, and member 2, 2, 1 is 0. So this stiffness coefficient is 0. K22 is this quantity plus this quantity. So we have 6042 kips per inch plus 81.6 kips per inch, and that's going to equal 6124 kips per inch. K23, row 2, column 3 is a 0 plus this quantity. So we have 0 plus 5874 kips, and so the structure stiffness coefficient is 5874 kips. Third row, K31, row 3, column 1 from member 1, and from member 2, row 3, column 1 adds 0. And so we have 5874 kips plus 0 equals 5874 is our structure stiffness coefficient. K32, from member 1, row 3, column 2 is a 0, and from member 2, row 3, column 2 is this quantity. And that gives us 5874 kips for this stiffness coefficient as well. And then K33. From member 1, we have this quantity, and from member 2, we have this. So we have 5,639,00 kip inches plus 5,639,00 kip inches again, and together we get the following structure stiffness coefficient. Now all other coefficients come from a single element stiffness matrix, or they are 0. So let's start assembling the structure stiffness matrix. And so we assemble our global stiffness matrix, which has 9 rows and 9 columns, and they'll be in degree of freedom sequence 1, through 9. And the rows will also be in degree of freedom sequence. Now from our calculations on the previous page, this coefficient 6124 kips per inch, then 0, and 5874 kips. Row 2, 0, 6124 kips per inch, 5874 kips. Row 3, 5874 kips, 5874 kips, and 1127800 kip inches. Now for the rest of the first 3 rows. The first 3 rows are forces at degrees of freedom 1, 2, and 3. The next column, deformation at degree of freedom 4, is connected by element 2, so we need to look in the element stiffness matrix to find the entries for column 4, as well as column 6 and column 7. So for column 4, degrees of freedom 1, 2, 3, we'll take these 3 entries. For columns 6 and 7, we'll take these 6. So we have 0, 5874 kips, and 281900 kip inches. Then columns 6 and 7. Minus 6042 kips per inch, 0, 0 minus 81.6 kips per inch, 0, and minus 5874 kips. For columns 5, 8, and 9, we need to look to the element stiffness matrix for element 1. And for column 5, rows 1 through 3, we want these coefficients. For 8 and 9, we want these coefficients. So for column 5, 5, 8, 7, 4 kips, then 0, then 281900 kip inch, column 8 minus 81.6 kips per inch, then 0 minus 5874 kips, column 9, 0 minus 6042 kips per inch, and 0. Now row 4. Row 4 refers to the force at degree of freedom 4 here at the end of member 2. So the coefficients will come only from the element stiffness matrix for member 2, and the coefficients for 5, 4, 8, and 4, 9 will all be 0 because no single member connects these 2 nodes. So for our member 2, row 4, our first 3 coefficients are given by these. Then our 4th column, 5th column is 0, then 6 and 7, and then columns 8 and 9 are 0. So we have 0, 5, 8, 7, 4 kips, 2, 8, 1, 9, 0, 0 kip inches. Then column 4, column 5 we said is 0, then 6 and 7, and then 8 and 9 we said are 0. Now row 5. Row 5 refers to the force generated at degree of freedom 5 here at node 1. And so we'll look at the element stiffness matrix for element 1 for all of its coefficients. And columns 4, 6, and 7 will be 0. So from element 1, row 5, our first 3 columns will be given by these quantities. 4 we said is 0, then 5, 6 and 7 are 0, and then these two, 8 and 9. So for row 5, we start with 5, 8, 7, 4 kips, then 0, and 2, 8, 1, 9, 0, 0 kip inches, 0, 5, 6, 3, 9, 0, 0 kip inches, 0, 0, minus 5, 8, 7, 4 kips, and 0. Now rows 6 and 7. We can obtain rows 6 and 7 because they are both at the same node, and so they will both come from just element 2's stiffness matrix, and the columns 5, 8, and 9 will be 0 coefficients for each of those 2 rows. So from element 2, rows 6 and 7, our first 3 columns are these. Then column 4, column 5 is zeros, 6 and 7 are these, and then 8 and 9 are both zeros. So that gives us a minus 6042 kips per inch and 0, a 0 and minus 81.6 kips per inch, a 0 and minus 5874 kips, a 0 minus 5874 kips, 0, 0 in column 5, and then 6042 kips per inch and 0, 0, 81.6 kips per inch, and then zeros. Now rows 8 and 9. Rows 8 and 9 refer to forces generated at degrees of freedom 8 and 9, and those coefficients will come from the element stiffness matrix for element 1. Columns 4, 6, and 7 will be all zeros. So from member 1, rows 8 and 9, our first 3 columns are these coefficients. Then 4 is zeros, 5 come from here, 6 and 7 are zeros, and then 8 and 9 come from here. So we have minus 81.6 kips per inch and 0, 0 minus 6042 kips per inch, minus 5874 kips, and 0. We said column 4 would be zeros. minus 5, 8, 7, 4 kips, 0. Columns 6 and 7 are zeros. 8, 1.6 kips per inch, 0, 0, 6, 0, 4, 2 kips per inch. Now step 3. Let's check symmetry. Would have been easy in this process to make a typographical error, and so one way to check that we have a quality stiffness matrix for our frame structure is to ensure first that the diagonal terms are all positive, and that they are, and that all of the terms mirror around that diagonal. So it's symmetric about that diagonal. So if we look at these two, they're identical. This one and that one are identical. Here and here, and these two, here and here, and these two, and the zeros, and these, the zeros here, the zeros here, these, and then this is the diagonal. We have this one and here, this one and here, and then zeros. Then in the corner and here, this one with this 0, then here with here, and this 0 with that 0. And we have the negative 6042, yes. This one matches this one, and then my line got a little bit of an extra gap. We move up to this one, matches here, and this pair of zeros. We have 0 here, and then this one with this one with this one, and then the diagonal. Here and here, then this quantity with this quantity, this pair of zeros. Here and here, this with this, the diagonal. Here with here, this pair of zeros, this one with this one, and this pair. So in fact it is symmetric, and we have reason to believe that we have correctly assembled the global stiffness matrix for our frame structure. Now let's go back and review the process we used to create this stiffness matrix. We started by assembling the stiffness matrix for each of the members, and to do that we had to find the length and directional cosines for the member, and then I calculated terms that show up on a repeated basis when assembling the member stiffness. We then used those terms like AE over L and 6EI over L squared along with the directional cosines and assembled the element stiffness matrix in global coordinates. First for member 1, then we moved to member 2, and with each of those member matrices we checked to make sure that the diagonal terms were positive and that the matrix was symmetric. We then added the two member stiffnesses to obtain the structure stiffness matrix, but we add them by degree of freedom number, and so for this particular structure only degrees of freedom 1, 2, and 3 are common to more than one structural member, and so for the 9 coefficients that refer to degrees of freedom 1, 2, and 3, we added them by hand and inserted them into the structure stiffness matrix. The remaining coefficients all came from just one member stiffness matrix, or were 0 because the degrees of freedom were not connected by a single structural member. We then finished by checking that the diagonal was all positive numbers and that it's symmetric about the diagonal. Now we can use this to find displacements, reactions, and member forces for this structure, which we do in later examples. Well done.